Welcome back, folks, to another exciting JLand Bio video. Hey, today we are focusing on the very last part of unit number 9, and that's going to focus on electrochemistry. Actually, I kind of lied. There's one more part to this I need to add that I will make a video on a little bit later, but we're really going to focus on galvanic or voltaic cells and understand a little bit about how we can couple reactions together. That is, we can take a chemical reaction that is thermodynamically unfavorable and couple it with a favorable reaction to actually push the reaction to take place. So it's actually really useful, and we'll be doing quite a bit of stuff with lab with this as well. So super exciting. Let's go ahead and move on. So hopefully by the end of today's video, you will be able to identify half reactions for anode and cathode, recognize electron flow in a galvanic cell, as well as utilizing a salt bridge. You should also be able to use standard reduction potentials to determine reduction under standard as well as non-standard conditions for this video. And hopefully be able to describe the relationship between cell potential, Gibbs free energy, and again, the value for K. That's the whole point of this unit, is really recognizing how we can utilize thermodynamic data to be able to evaluate K and determine shift with Le Chatelier's principle. So understand that when we create a voltaic or a galvanic cell, that we are using spontaneous reactions, and that helps us create electrical current in two separate compartments. One is known as the anode and the other is the cathode. This should look familiar to you. We're just going to dive in a little bit deeper and explain a little more about what's going on here. So we're going to use zinc and copper for this reaction. Zinc is your anode. That is the site of oxidation. Okay, and that anode becomes smaller. So you look here, you have your zinc anode on the right hand side here. There's a piece of metal that is in solution. That piece of metal there is your electrode. As the voltaic cell runs, it is going to be oxidized. That is, it is going to become smaller, because solid zinc, that is the zinc that is on the electrode, is going to become zinc ions as it loses electrons. Remember, oil rig oxidation is losing, so it's going to lose those electrons. Copper, on the other hand, on the opposite side, is the side of reduction. It is going to gain those electrons. So it is going to become larger over time because the electrons move through the wire from zinc to copper. Once it reaches copper, then it reacts with the copper ions that are in solution to form solid copper. So the cathode is going to become larger, and the anode is going to become smaller over time. Now, it's possible to use other electrodes. You can use inert electrodes when a gas is involved, or if the reaction is ion to ion. So in order to prevent the redox reaction from occurring in solution, so if you take a copper wire and you place it into silver nitrate solution, you guys have probably seen this before, that the solution will turn blue, and that silver actually appears on the copper wire, and that's a redox reaction that's occurring within the solution. Well, we don't want that to happen here, because we want the electron flow not to go from the metal into the solution, but rather we want it to go through the wire. And so in this case, what we do is we use a solution of the metal's own ions. So for example, if you look at copper, the copper cathode is actually placed into copper sulfate solution. This prevents redox from happening in the solution and allows it to occur through the wire. To complete the circuit, because anytime we do something with electricity, the circuit has to be complete, we add what's called a salt bridge, and that salt bridge is kind of in the middle there, and it typically contains soluble salts that will not react with the solutions. We don't want anything in there to be able to react with the metals that are involved, or anything that will react with the anions that are found in solution. The anions that are found in the salt bridge actually flow towards the anode, so you can see the anion is sulfate and it is flowing toward the anode. And the reason for that is that we are producing more zinc ions in solution on the right-hand side, and therefore we need to be able to balance out those charges by having the sulfate move towards the right-hand side. Basically, it keeps an electrical potential and allows for electricity to continue to flow. Cations are going to flow towards the cathode, because you are removing the cations by having the copper being reduced. And so the sodium ions are going to move towards the left-hand side. A wire and a voltmeter, you just connect the anode and cathode together, and that allows the electrons to flow from one side to the other. So how do we know specifically what is being oxidized and what is being reduced if you're given a type of problem where it says, hey, use copper and aluminum, or hey, use copper and silver? Well, what we do is we look at the standard reduction potentials, and this is a chart that will be given to you, or the values themselves will just be given to you. The most negative species on here is going to be easily oxidized. Meanwhile, the most positive species are easily reduced, and that will be the cathode. So your most negative species is going to be your anode, and the most positive species is going to be your cathode. And again, we're looking at the electrical potentials on this chart here. So if you look at the value for E, you will find that, like if we were using, for example, copper and zinc, you would see that zinc has a more negative species at negative 0.76, and copper is more positive at 0.34. So zinc is going to be your anode, and copper is going to be your cathode. So again, we're going to look at that example, zinc and copper. Again, zinc being reduced is a negative 0.76, so this is the most negative of the two, so it is at the anode. And copper is going to be your cathode. Now remember that these are reduction potentials. Okay, all of them that are listed there are reduction potentials. So because zinc is at the anode, zinc ends up being oxidized. So we have to actually reverse the equation. So if you take the arrow and flip it, you would also flip the sign of your E value. So keep in mind that the E value of the total cell is the oxidation value for E and the reduction value for E, and so you simply just add those two together. Remember that zinc is being oxidized here, so we flip the sign. So it's 0.76, so we're going to add that to 0.34 and get 1.10 volts. And that is your electrical potential for the entire cell at standard conditions. So long story short, how do we go through and figure all of this out? We write the half reactions from the reduction chart and the voltages. Remember that the most positive E occurs at the cathode and the most negative E occurs at the anode. Remember that you reverse the anode reaction and change the sign of E. You balance the half reactions and then do your calculation. It's pretty straightforward, but let's do one practice problem together. So let's go ahead and consider the galvanic cell based on the reaction that is given here. Okay, we've got 3 plus for aluminum plus Mg solid yields aluminum and Mg2 plus. So we're going to draw the galvanic cell for the reaction. Calculate the E electrical potential for the cell and then write the balanced chemical equation here. Okay, because again, charges here are not balanced. So the first thing we need to do is we need to take a look and figure out what's being oxidized, what's being reduced. So here we have Mg, and Mg here is going from a 0 oxidation number to a +2. So we're going to say that that is losing electrons, and therefore Mg is being oxidized. So that's going to be at our cathode. So I'm going to draw this out. I claim to be no artist. Okay. So this is going to be our magnesium, and this is going to be our aluminum. Okay, we're going to connect it with a wire. Have a nice little voltmeter here. Don't forget your salt bridge. We'll just put in some NaCl. This right here will make magnesium sulfate. And here we'll make aluminum sulfate. Electrons are going to flow this direction, because remember they go from anode to cathode. Okay, pretty straightforward there. Let's calculate the E potential for the cell. I'm going to have to get out a chart. So let's go ahead and write out our half reactions here. So Mg is a solid. Then go to Mg plus 2 aqueous plus 2 electrons. And aluminum is going to be reduced. Now the potential for Mg, our reduction potential, is negative 2.37. And aluminum is negative 1.66. Remember that with whatever's being oxidized here, which is magnesium, we're going to flip the sign. So it's positive 2.37 plus negative 1.66. We plug that into our calculator to get our E cell. It's 0.71 volts. All right, now the last bit asks you to write a balanced chemical equation. I'm going to go ahead and clean this up real quick so that way we can do that. So we have our half reactions here. One thing we need to make sure we do is that we make sure that all of the electrons in this cancel out. Okay, so we have 2 electrons here and 3 on the bottom here. So what we're going to do is we're just going to take this, multiply this by 2, take this, and multiply this by 3. Okay, and so these are going to cancel out, and then what we end up with is our balanced equation. So we end up with 2Al plus 3 aqueous plus 3 mg solid yields 3 mg 2 plus aqueous plus 2 Al solid. And that's our balanced equation there. Okay. So again, not too difficult. Just take your time, go through it, and read each question very carefully, okay? Follow the directions, and you guys will be in good shape. Let's move on. So a big important question that we need to make sure that we ask is why does this reaction actually happen? And it all goes back to delta G. It is spontaneous, this particular reaction. Delta G is negative. And we utilize this in a formula where delta G is equal to negative N F times E, where N is the number of moles of electrons that are transferred. F is Faraday's constant, and E is your cell voltage. So if you think about it, if the E cell is positive, you plug that number in there, then delta G is going to be negative, and the reaction will be spontaneous. If your E cell is negative, you plug that number in, two negatives make a positive, so then delta G is positive, and the reaction is non-spontaneous. Okay. So it's really just trying to think about this, plug all these numbers in, be able to solve. Again, we can utilize this formula very easily when we're looking at voltaic or galvanic cells. So let's do a practice problem and see where we're at. Okay, so let's take a look at a little bit of a challenging example here. It says, predict whether 1 molar HNO3 aqueous will dissolve solid gold to form a 1 molar Au3 plus aqueous solution at 25 degrees Celsius. And these are the relevant half reactions. So this is where this gets a little bit tricky, because I'm not really just telling you to build a battery and go from there. I'm giving you a specific condition, and that is that I want to take solid gold and form an Au3 plus solution. Okay, so what that means is that I want to take gold in its solid form, and I need to form aqueous ions of gold. I want to dissolve it. Okay, so in that instance, it forces us to say that this must be oxidized. This must be our anode. Okay, so do keep that in mind. This is, like I said, it's giving you a specific condition here. It's not telling you to just build a battery. If you're to build a battery, obviously you go with the lower potential as your anode, and then your cathode is the higher value here. But because we're specifically wanting this, we've got to make sure we go through it this way. Okay, so if we take a look at this and go through it just like that, okay, the potential here, because remember this is being oxidized, so we're actually going to kind of reverse what this is, because remember these are reduction potentials, so that's negative 1.50 volts. Our other equation, which is given up here, I won't rewrite it, but that's going to give us a positive 0.96 volts. Okay, and so if we go through and we calculate this and we do the math here, we're actually going to get a negative 0.54 volts for our E cell. Okay, so it gives us a negative value. So if we plug that into our Nernst equation, right? We plug that into our Nernst equation, negative value here times a negative value gives you a positive delta G. Remember that with our positive delta G, reactions are not spontaneous. Okay, again, positive delta G for that reaction, not spontaneous. However, we can go through and we can continue to calculate this just to be sure by plugging the numbers into delta G. So we just say delta G gives free energy. The number of moles of electrons transferred here is 3. So 3, we're going to multiply that by Faraday's constant, which is 96,500 coulombs per mole. Then we multiply that by our negative 0.54 for our E cell value. And delta G here, when we finish our calculation, is going to be 1.56 times 10 to the 5th. Okay, which is a relatively positive delta G value, about 15 kilojoules. And as a result of a positive delta G, we would say that this is not spontaneous. So this will not work. Okay? So you would not be able to dissolve solid gold using 1 molar HNO3 solution. Okay? Again, pretty straightforward there. Let's move on. So everything we've been looking at so far is at standard conditions. Okay, standard conditions implies that things are at a 1 molar concentration. So what do we do when things are at not standard conditions? What happens when the concentration changes? And what's nice is you can actually really think about this in terms of Le Chatelier's principle, in terms of concentration of ions, because in essence, this is a system that is at equilibrium. So if we think about this, let's say that Zn plus 2 ions is 1.50 and copper is 0.50. Well, the concentration of zinc is higher. So Le Chatelier's principle says that it is going to shift to the left. If equilibrium shifts left, then that means that the forward reaction here decreases, so our E cell value is actually going to go down. Okay? Because we're not getting the same movement of flow of electrons going from reactant to product. Okay? Because again, the reaction shifts to the left, so the forward reaction is going to slow down because the reverse reaction is going to increase. Same thing if we look at the next part of the problem. We have an increase in copper, so we have an increase here. We have a decrease of ions on the right-hand side, so that's going to cause equilibrium to shift to the right. Which actually causes our E cell potential to go up. Okay, kind of a different concept here. What if I add NaOH? What if I added a base to copper ions? Well, if we remember, we talked about how acids and bases impact solutions here. So if I add OH here to my copper plus ions, that actually reduces the number of copper ions in solution because Cu and OH are going to react, right, to produce the weak base here. Because remember, weak bases do not completely dissociate, so they are going to react to form the base itself. So copper ion concentration goes down. And if copper ion concentration goes down, then equilibrium shifts to the left. Okay, just kind of like the stuff we've been talking about with changes in equilibrium. So do keep in mind that when concentration changes, we can actually get small, I would say insignificant, but small changes in our E cell values. And we can go through and actually calculate those as well. Again, if we look at this new equation here, we have our Nernst equation, which is the E value for the cell. Remember, when we don't have the little degree sign up at the top, that means that it's not at standard conditions. So our E cell value here is going to equal our standard condition E cell value minus RT divided by NF and the natural log of Q. Okay, so we can go through and figure this out pretty well. Let's just kind of start writing things out as we go through. We do need to keep in mind Q, remember, is products over reactants. So in that case, it's going to be the concentration of our zinc ions divided by the concentration of our copper ions. All right, and then we can just kind of plug these numbers into this equation here. So we have E cell equals the E cell for this particular reaction. If you remember, we go back, we calculated this previously, is 1.10. And again, you can calculate that fairly easily utilizing the reduction potentials. We're going to subtract R, again, 8.31 times T, so 298. N, the number of electrons, or moles of electrons transferred, which is 2. F, which is Faraday's constant, it's 96,500. Multiplied by the ln of Q. Remember, Q is given to us there, so concentration is 1.50 over 0.50. Okay, so a little more math involved here, but what you end up finding is kind of interesting, is that even with all this change, the potential only changes 1/100th of a volt. Okay, so you can plug those numbers in, solve. It's like I said, it's just a pretty straightforward equation. Remember that this is at non-standard conditions, and remember, non-standard conditions occur when the concentrations are different. Okay, and again, if you think about Le Chatelier's principle, it makes it really easy to determine if we're going to get more reactants, more products, that kind of stuff out of the equation. So take a look at this. This is a little bit different type of problem here because the cells themselves actually have the same ion that's associated with it. So this is known as a concentration cell. Basically, it uses the concepts related to Le Chatelier's principle in order to determine, in order to make electricity flow. Okay, so if we think about Le Chatelier's principle here, we need to first determine the anode and the cathode before we figure out any electrical potential for this cell. Okay, so the first thing we want to look at is that we have a low concentration here and a high concentration on this side. Okay, so what that tells us is that equilibrium is actually going to shift this direction. Okay, and if equilibrium shifts that direction, it means that we are going to be making more ions in solution. It needs to make more ions here, and ions need to be used here okay. So here on this side, if we are making ions, then as a result we are losing electrons. So this cell right here has to be your anode, because that is where more oxidation is going to take place. And this is going to be your cathode, because this is where more reduction takes place. Okay, so again, it all boils down to Le Chatelier's principle here. Now what's interesting is that the anode and the cathode are both iron, and so the reduction potentials for both are the same. It's negative 0.44. We flip one, so we get positive 0.44. So in order to determine our E cell, it's 0.44, negative 0.44 plus 0.44, so our E cell is 0. So again, if I want to know the potential for this, I just do the exact same thing I've done before. The only difference is that we need to make sure that we keep in mind that the E cell value is going to be 0 for this, or the E cell at standard conditions. So with this, we're going to get E cell equals E cell at standard conditions. We're going to subtract R times T. We'll just assume it's at 298. Okay. Number of electrons being transferred is 2 times Faraday's constant. And then we're taking natural log and just follow the same rules we did. Remember, we calculate Q. And what we get here is a very small difference of 0.03 volts. Okay. So again, just a couple different ways we can go through and calculate these things. We will go through this in class as well, but like I said, just kind of keep those things in mind, all right? Hey guys, we literally got through about 80% of electrochemistry there, so just keep those things in mind. Be able to identify half reactions for anode and cathode, electron flow, salt bridge, standard reduction potentials, all that good stuff. We'll talk to you later, guys. Have a great day. Make sure you like, subscribe, leave a comment down below, and we will talk to you later. Bye-bye.